Let's look at exercise 25. We are integrating from 0 to pi over 4, 1 plus cosine squared over cosine squared. So here again is an example where we need to split up this fraction into 1 over cos squared theta plus 1 cos squared theta over cos squared theta. And again, don't leave off the d theta. It's absolutely necessary. And then we can remember that 1 over the cos squared of theta is actually secant squared theta. And again, using the properties from section 5.2, we could split this into two integrals, the integral of secant squared from 0 to pi over 4 plus the integral of 1 d theta from 0 to pi over 4. Or we can combine it like, do it here as a sum in one integrand. Either way is fine. So whose derivative is secant squared theta? Or look in your table of antiderivatives, and in fact the derivative of tan theta is secant squared theta. So that's my first term antiderivative. And the 1 is really like theta to the 0 power. So whose derivative is 1? That would be theta. And then again, I put the vertical bar with my limits of integration on it. So now I can plug in, and here I will, in the previous example, I separated into two. Here I'll keep them together so you can see both ways of doing it. So I can plug pi over 4 into both of these terms, minus plug 0 into both of these terms. So the tangent of pi over 4, I don't know if you remember, is 1. And the tangent of 0 is 0. So this all nets out to 1 plus pi over 4. And you could combine that into a single fraction if you want. Doesn't really matter. You could get a decimal if you'd like as well. You're welcome to graph the integrand function and try to relate this 1 plus pi over 4 to the area under the curve. All right, and then in numbers 53 and 54, we can start to understand why integration is important. What actually does this integration tell us in a context? So if oil is leaking from a tank at a rate of R of t gallons per minute at time t, so this is a rate, notice the per minute, then the integral from 0 to 120 of R of t dt, what does that actually stand for? So first of all, this 120 is in minutes because t is in minutes. So the 0 and the 120 are t values, and so that's 120 minutes is the same as 2 hours. So if we integrate the rate of change, what we actually get is net change. So this integral is the gallons, not gallons per minute, gallons of oil leaked over those 2 hours from time 0 to time 120 minutes. So you can think of it as R of t is in gallons per minute times time dt is in minutes. You can think of dt as a change in time. And so when we multiply, right, we're getting height. If you think of the R of t curve that has gallons per minute on the vertical axis, think of the rectangles we created. The heights of the rectangles are in gallons per minute times width in minutes. And so the area under the curve gives us gallons. And in general, when we integrate a rate of change, we get net change.